All right, students, today let's start by discussing the basic concepts of cryptography. In our previous lessons, we briefly introduced the types of threats we might encounter in our networks and how we should respond to them. Among these, cryptography is very important. Okay, let's first look at cryptography here. Here, there are a few basic concepts in cryptography. When we were discussing security earlier, during our network security talks, we actually mentioned one thing about confidentiality, integrity, and we also talked about availability. But from the perspective of cryptography, we not only need to ensure its confidentiality and integrity, but there are also two more things: source authentication and non-repudiation. That is to say, if we want to solve our problems with secure communication, then here, if we use modern cryptography, it can achieve confidentiality, integrity, source authentication, and non-repudiation. These aspects, we will discuss these later. We will analyze this. Cryptography is also known to some as cryptology indeed. Cryptography and cryptology, mainly it is about cryptology. But here on the contrary, from the perspective of an attacker, how do they break encryption? That is, here by using technical means to analyze passwords, and this is the reverse, right? Cryptanalysis is by studying what kind of vulnerabilities and weaknesses to break these encryption technologies. They are like the shield and the spear. That is to say, you have cryptography, right? Then I have cryptanalysis. You have cryptanalysis, of course, I also can update my encryption mechanisms. So here is about our cryptography and cryptanalysis. Here, technically speaking, they are in a spiraling rise. Okay, so this place in cryptography here, it's about confidentiality, integrity, source authentication, non-repudiation. These things honestly are our goals. But to achieve these goals, we definitely need some tools. In modern cryptography, they are usually called algorithms. This, speaking of algorithms here, means when we talk about algorithms, we must mention another concept called classical cryptography. One is classical cryptography and the other is what we now call modern cryptography. What's the difference between the two? In classical cryptography, it does not really have what we call algorithms. It's more of a mechanism. That is to say, encryption. Now we say it has algorithms. These encryption algorithms, more in some sense, in a certain sense, in terms of meaning, are more like a mechanism. In classical cryptography, it uses a mechanism to encrypt our data, which means encryption is actually a process of turning plain text into ciphertext. Turning plain text into ciphertext, this action is called encryption, and conversely, if you have encryption, you must have decryption. You turn what's understandable into something that's not. Then, if the other side wants to retrieve the plain text, we need to perform decryption. Decryption then is the reverse process, turning ciphertext back into plain text. If you have encryption, you must have decryption. But if you have only encryption without decryption, what do you call that? I think it's more like shredding, right? Once encrypted, it cannot be decrypted. If you encrypt a file and nobody can decrypt it, what's the difference between that and shredding, I think? There's no difference. It's like, say, some companies, after their servers are decommissioned, they have to take their hard drives and then write gibberish into them, overwrite them several times, after covering them up, then physically destroy them. That kind of thing, honestly, you go and overwrite gibberish onto a hard drive, making it incomprehensible, changing the understandable data into something incomprehensible. That's not called encryption because it can't be decrypted. That's why. Why? Because it can't be decrypted. That is to say, encryption must have that. Encryption and decryption must coexist. If you have encryption, you need decryption. So-called classical cryptography means you use a mechanism to turn plain text into ciphertext. That kind is called classical cryptography. For example, for instance, let's give an example, an older one, the Spartan Cytel. It should be well known the Spartan Cytel, this thing is just a stick. Just this stick. You take what should be a strip of leather, and you wrap this leather around the stick. And then you write some information on it. Then you pull the strip off. Write some of that intelligence on it. Then you pull the leather strip off. Once it's off, honestly, we can assume that the letters have been scrambled, and after scrambling, others probably can't understand it. But honestly, such ancient methods, dating back thousands of years, almost in our terms, roughly during the spring and autumn period, around May, about that time, such old encryption, I think it's not worthy of being called an algorithm. It's just a mechanism. Although it scrambles the letters, making them unreadable. Honestly, firstly, for alphabetic languages, it might still work, but for our kind of pictographic languages, others might still guess what you wrote on it. Even I think because of the high illiteracy rates back then, people might not even understand plain text. So this kind of thing, once you know its mechanism, right? Once you take out a stick similar to it, you can crack it. And once it's cracked, that encryption mechanism can't be used anymore. That's the way it is. Classical cryptography is just like that. So then, like us, or let's put it this way, the Spartan Cytel, we think it doesn't qualify as an algorithm. So these older ciphers, like the Caesar cipher, simply put, is a transposition. It scrambles the order of the letters. For instance, it scrambles ABCD, right? And after scrambling, it becomes CPAT, something like that. It does transposition, like swapping the first position with the third, this simple substitution. Indeed, it can achieve the purpose of encryption, but this type of substitution, if someone learns your rule, to put it bluntly, you can no longer use it. So, this type of classical cryptography, because if your encryption mechanism is known, you have to update it. As a result, if you play it this way, you have to keep changing your encryption methods, constantly evolving. In short, you don't have a mechanism that can be used for a long time. That is classical cryptography. So if your system is known, then your whole encryption scheme can be overturned and can't be used anymore. What is the difference between modern cryptography and classical cryptography? Well, it includes an algorithm and a key. Here, the algorithm is public. Algorithm is public, key is secret. The key is kept secret, which means in modern cryptography, when we perform encryption, it requires a key. The algorithm, the thing about algorithms, everyone knows it's public. Then, we, when encrypting, need to use a key. And if the key is compromised, or if you feel the key is no longer secure, you just need to change this key, which means in modern cryptography, its encryption mechanism generally doesn't need to be changed. We just need to change the key. That's why we mostly study modern cryptography now. Okay, so this so-called encryption, mainly in modern cryptography, mainly addresses confidentiality. But having just confidentiality is actually useless, because after you convert plain text into ciphertext, others can't understand it. And if there's an attacker who simply wants to cause disruption, they make it so you also can't understand it, right? After they intercept your ciphertext, make a slight modification, even changing one bit, you can't decrypt it anymore. And moreover, such encryption and decryption definitely require the use of some of your device's performance. At that time, if such tampered ciphertext is unusable in calculations because of the algorithm, ultimately, calculations are required. If tampered ciphertext is used in calculations, it will definitely either produce a result that is a bunch of meaningless gibberish, or it will cause the processing to crash while you're calculating. So this kind of issue is really annoying and frustrating. So what do we do? Well, if that's the case, is there a way to ensure data integrity? Let's first check if the data is intact, right? Then we check whether there's an issue with its confidentiality, Like, for example, say you write the ciphertext on a piece of paper and then you place it inside an envelope and send it out. When the recipient checks it, they look to see if the envelope has been opened. If the envelope has been opened, it could mean that it has been tampered with, and if so, it's disregarded. So we can use certain mechanisms to ensure the integrity of the data. The so-called hash algorithms or hash functions are essentially used to ensure our data's integrity. So hashing or hashing algorithms are basically used for that purpose. Here, in this area, the algorithm has very distinct characteristics. For instance, in our everyday life, we might not say in everyday life, but when we use computers, we often come across something called MD5, right? So this is called Message Digest 5 or MD5, which belongs to hash algorithms, and it is used to ensure data integrity. So what is its mechanism? First, it is a one-way function, non-invertible, meaning it's a one-way function where we compute a result from the original text. But you cannot derive the original text from this result. That's the first point. Secondly, it handles variable input sizes, meaning everything is hashable. That is, everything can be hashed in that. In the digital world, everything is hashable. After all, in our computers, everything ultimately converts to binary, right? So, it appears that everything is digital, meaning in the digital world, everything can be hashed. In our systems, anything can be processed through the hash algorithm to produce a result. In this way, it's not picky. Anything can be hashed to compute its digest value, which is a fixed length value. The length of the digest depends on the algorithm used. Some people also refer to it as a fingerprint. That means you take an original document, input it into the hash function, and then it calculates. No matter how long the original text is, it always returns a fixed length output, and at this time the output will differ if the input text differs. This leads to collision resistance, meaning if the inputs are different, the outputs will not be the same. Another feature is called the avalanche effect, which means even a slight difference in input leads to a significantly different output. Another point is that I have a small software here, which is used for calculating hashes, just a small piece of software I found online. Now let's do something. I'll create a new text document. I'll just create a text document. Remember how we opened a web page earlier? No problem. I'll just select all, copy, and paste. We don't care what it is anymore. I save it, and at least for now, it is a plain text document, right? Okay, text document. We'll use this document to compute a hash result. Here's the MD5, for instance, and here's the result. Now, regardless of the file name, the computed result is here. This is the result it computed. Now, no matter what you call this file, the computed result will be the same as long as the file content doesn't change. The results will be the same, even if you do this. I'll create another one. I'll copy the original text, paste it here, and save it. Save. I'll calculate again. It's still the same. Still the same, right? Okay. Now in this way, what I do is come here, and at the end, I add a space. I've just added a space. Nothing else. I'll save again. After saving, I'll check which one did I just save. Is it this one up here? Check the time. It's 1919. What's the font size? 1920. It should be the one below, I guess. Let's open it and see. Is there a space? There's a space. Notice anything? Do these two have anything in common? The only similarity is that both are in hexadecimal, but honestly, you can see right away that they are different, right? This is called the avalanche effect. Even a tiny change in the original text, just a change of one space, causes the hash result to change drastically. Now I'll delete that space. I'll calculate again. After removing the space, you'll see the result matches the original again, right? So we can use this hash algorithm to verify the integrity of our data to ensure that the data hasn't been altered. based on several principles, one being the one-way function. This hash isn't compression. No matter how large the input, the hash output is fixed length according to the algorithm. If it's MD5, it's always 128 bits. If it's SHA-1, then it's 160 bits. We can see here the SHA-1 value, right? 1388, 1388. The 0F9 earlier was because we added a space. After deleting it, it's again 1388. This shows that no matter how long our data, the results are consistent. Now, if I do this, I copy it, paste it several times, paste it multiple times, and then compute the hash again, the length remains the same. Though the length may not look the same, but the results will be consistent. Each digit is hexadecimal, and at this point, the length remains the same. Here it totals 128 bits. Regardless of the length of your input, no matter how long it is, the resulting output is always fixed in length, even if we do this. How do we handle it? I'll open. Over here like this, I'll open a large file. This one should be big enough, right? This file is huge, a gigabyte file. It's a Cisco 3A server's ISE installation image. I'll throw it in here. It might calculate a bit slower because it's so large. Why am I calculating this thing? The file name of this file is called this, ISE 3.1 something or other. Then next, like this, I'll go to this Cisco official website. Go software. You could directly go to software.cisco.com as well. We're automatically redirected to software.cisco.com. After arriving here, we browse everything, all of it. We find the security section. Under security, security management. I'm not sure what it is. It's right here, under network visibility and segmentation. This section has the Identity Services Engine, abbreviated as ISE. Click Open. After opening, over here our version is 3.1, right? We chose 3.1. In 3.1, inside 3.1, let's see what this section is. It's something like 3.1.0 whatnot, 518b. This way, if we go this way, these are patches. Keep going down, keep going down, keep going down. Actually, let's search here first. Click on the ISO. There are a few ISO options. It seems to be this one. Let's check if the name is the same. Yes, the names are the same. The names match. Now let's hover the mouse over this area. We can see there's an MD5 checksum here. Let's copy it. After copying, paste it. Paste it here. Then, this is what we see online, what we downloaded from the internet. Another thing, we have this, which we just calculated ourselves. Has anyone noticed these two are case insensitive? Why? Because they are hexadecimal, right? In hexadecimal, RR represents 10 and so does lowercase a. They represent the same value. This means what? The calculated results are the same. So what does this prove? It proves that the image on my computer and the one we downloaded from the internet are exactly the same, undamaged, right? We can verify the integrity of files this way. So when a file is transmitted, whether it's being downloaded or uploaded, during file transfer, we can verify the file's integrity using this method. We verify the file's integrity through this algorithm. This algorithm is where everything is hashable. All things we have in this system can be input into this algorithm, and then it's absolutely irreversible. If you say you could find a way to put it this way, if you can find a way to find a method to take an actual file this big and reduce it to just this length and still restore it, I think you should be on the Forbes list. You lengthen, right? You lengthen 1 bit, the possibilities double. So in this case, you really can't completely avoid it. It can't be avoided. But often that among files with real practical significance, we can avoid collisions. But honestly, like we just said about MD5, MD5 has actually been cracked. By whom? By him, he cracked it. I remember he is now an academician. At the time, a professor from Shandong University cracked what? He cracked MD5. But this crack wasn't an absolute breakthrough. It was just about creating a collision. You create a file. Let's say this file is file A, and then you make another file. This one is file B, file A, file B. And then through some operation, you create two new files. And these two files can compute the same results, meaning you take the original file and deliberately manipulate the file A and file B, make some modifications to it, turn it into two new files, and then these two new files, like this file is called A1, and this one is called B1. A1 and B1, when their hashes are calculated, can collide. But honestly, if you're really going for a collision, you must be doing it deliberately. You're doing it on purpose. In reality, when we use hashing, no one does this. Who in their right mind would do such a thing? Right? Like, if you were to offer a file for download online, you're setting up this scenario yourself. Honestly, no reputable site would engage in such activities. Honestly, no legitimate website would do such a thing. So, this, like MD5 or even SHA1, although they've been cracked, it's not that severe. Because, basically, no one of good repute would exploit this bug. But from a security perspective, since the algorithm has been cracked, we should use something else if possible. However, like our hash algorithms, the longer the digest you compute, the more resources you'll need. Like SHA, it has two series. SHA has one called SHA1 and another called SHA2. SHA1 is 160 bits and SHA2 is variable length. Variable length, like for instance, SHA256, SHA384, SHA512, etc. So, when choosing a hash algorithm, we try to choose the longer ones. As long as your device's capabilities and knowledge can keep up, try to pick the longer options. These scattering algorithms, as our colleague just introduced, are usually used for integrity verification. Like MD5, MD5 is fixed at 128 bits. SHA1 is fixed at 160 bits. And SHA2 is fixed with variable lengths, like SHA256, which generates a digest 256 bits long. SHA384 means the digest is 384 bits long. SHA512 then generates a digest length of 512. The longer the digest, the better the collision resistance, but the more computational resources it consumes. They all use the lightning function. So here, this place has MD5, it has SHA1. Now, if I use this tool, so on the official website, right, over there, it also provides us with an MD5 and a SHA512. So looking at it this way, now, if I want to use this tool, then I can only use MD5 for verification because the other algorithms are not supported. So sometimes you see, when using this hash function, it often employs multiple algorithms for calculation to ensure compatibility. This utility, as we've already demonstrated, allows us to verify file integrity. After downloading the file, we proceed to verify this MD5. After the verification, we compare the verified MD5 with the one published on the website. If they match, it means it has not been tampered with. But if they don't match, that means it's likely that the file was damaged during download. Sometimes, especially those multi-threaded downloads, a file you download using multiple threads, right? It's quite likely that the file could be damaged. So we can use this mechanism. To perform verification. All right. The second use is for authentication. But is authentication that simple? So to say, authentication involves introducing something called HMAC, which stands for Hash-Based Message Authentication Code. Typically, speaking from the perspective of the network, there would be data packets in the network, of course. All right. To ensure data integrity within the network, shouldn't we ensure the integrity of the data packets? Ensuring packet integrity. All right. If you want to ensure packet integrity, you'd say, originally, I have a data packet. I take this data packet and create a hash of it. Then take this hash calculation. And on this left side here, say A. And on the right side, BIA. Package it this well-packaged data packet. At the front, there's the IP, this place. Then IA, hand over the well-packaged data packet to B, then based on that original packet, right? The contents inside the packet are used to calculate a hash. If the results from both sides match, it indicates that the packet hasn't been tampered with. But if the calculated hash result differs from what's written in the packet, it might have been tampered with. However, at this time, now a bad actor has appeared. This bad actor is C. At this time, regarding the packet sent by A ended up with C. The packet sent by A ended up with C. C, through a man-in-the-middle attack, hijacks this packet, and then C looks at this packet. C looks at this packet, right? Okay. Then I will tamper with your packet. I will tamper with this packet. After tampering, no worries. I will recalculate a hash. I will calculate a new hash and then send this packet to B. At this time, B naively checks the original packet's hash and sees it matches the hash result. The hash result matches. He thinks the packet hasn't been tampered with, but is that the case? It's not, right? Because C knows, right? After I tampered with the packet, I at least recalculated the hash result. By doing this, you indeed cannot guarantee that the packet hasn't been tampered with. So, what to do? At this time, we can do this. A and B, they agree on something. A says, my word, there should be a key here. The packet sent by A ended up with C. C, through a man-in-the-middle attack, hijacks this packet, and then C looks at this packet. C looks at this packet, right? Okay. Then I will tamper with your packet. I will tamper with this packet. After tampering, no worries. I will recalculate a hash. I will calculate a new hash and then send this packet to B. At this time, B naively checks the original packet's hash and sees it matches the hash result. The hash result matches. He thinks the packet hasn't been tampered with, but is that the case? It's not, right? Because C knows, right? After I tampered with the packet, I at least recalculated the hash result. By doing this, you indeed cannot guarantee that the packet hasn't been tampered with. So, what to do? At this time, we can do this. A and B, they agree on something. A says, my word, there should be a key here. What it means is, during authentication, telling someone directly what your password is, to be honest, is still unsafe. If both sides are performing authentication, honestly, it's not safe. If both sides are performing authentication, you hash the password and send that hash result over, because the same hash result means we believe the original text calculated is the same. For example, if you hash wolf and give it to the other side, then the other side also calculates a hash to see if it matches the original. In this way, we can know, right, if the other side's key matches mine. Through this method, we can perform key authentication. Usually, in network communications, we often don't send keys in plain text. You see, using encryption, to be honest, is not as secure as using this type of hash, because hashing is irreversible, right? With encryption, there's decryption to consider. So when you send this hash result to the other party, even if it's intercepted, it's of no use, right? The plain text might be intercepted, but if it's just the hash result, intercepting it is useless. In this way, the other party, in this case, even if a man in the middle intercepts it, it's of no use because the middleman doesn't know what the key is. Of course, if you're not performing authentication, if you want to use it to ensure data integrity, then you need to hash this packet, right? You must include the key in our rules. Since the middleman doesn't have this key, he can't compute a hash result convincing enough for the other side. So by using HMAC, we can ensure data integrity and also protect passwords. The security of passwords during authentication can be ensured this way. So what is HMAC? It's a keyed hash message authentication code that requires both parties to have a shared secret key. Through it, we can achieve source authentication and integrity verification. As we mentioned earlier about confidentiality and integrity, source authentication, non-repudiation, source authentication refers to verifying whether your counterpart is legitimate. When you meet, you need to ensure the other party is not an imposter. Here, by using HMAC, we can achieve this. If you use HMAC, you assume the other party has the same pre-shared key, right? So you believe the other party is on your side. It's somewhat like matching codes and responses at a secret meeting. This side, A says to B, "The emperor covers the earth tiger." B responds, "Little chicken stewing mushrooms." Then it's generally like this. If suddenly someone counters A with, "You're too beautiful, chicken," and B says little black, then you see they are not one of us. So remember about hashing. While hashing can ensure transaction integrity, if we speak from the perspective of network communications, if we want to send the original message along with the hash result, at this time, we cannot just send it out directly. We must include a key. We must take this original text along with a key to perform the hashing. This way, a man in the middle can't perform the same computation. This is what HMAC is. Hash message authentication code. So the hash result calculated from the original text along with the key. At this time, we can use this in routing protocol authentication, like for instance in protocols like EIGRP, OSPF. These routing protocol authentications. Because our routing protocols need to ensure security, since we've previously talked about something called root injection. Any random routing protocol fears this kind of incident. Suppose an attacker directly connects a device to our network and negotiates with our network devices to establish a neighboring relationship under this routing protocol. Then he injects roots into our network to hijack packets, which can severely affect our network security. So, what do? We need to authenticate, right? At the very least, we can ensure that devices establishing routing protocol neighbors are legitimate. What do we mean by legitimate devices? We can introduce a key inside. In this case, if we decide to use this hash authentication, it will perform a hash calculation with this key and carry the result in the packet for interaction. When you receive a packet from a neighbor, we need to verify this hash result. If we use this key to calculate the hash result, and if the calculated hash result matches the one carried in the packet, then we believe that the packet has not been tampered with. Or rather, moreover, it's not just about the packet being untampered. We believe that the neighbor's identity is legitimate if the packet is legitimate. Specifically for different routing protocols, it is about authentication. Authentication mechanisms vary across different routing protocols. Let me give you an example. For protocols like OSPF, each and every data packet requires verification. For a protocol like OSPF, every single message must be verified if authentication is configured. Now, consider a protocol like BGP, like this. BGP type of protocol. In the case of BGP, it verifies during the establishment of neighbor relationships verification. Why? Because BGP's HMAC verification mechanism isn't actually part of BGP. It's part of TCP, within which there's an option 19. Option 19 specifically is used for conducting an MD5 verification. So in BGP, this feature borrows TCP's option 19 for verification. Option 19 is used for verification. In BGP, we can set a password for each neighbor. This is done during neighbor establishment, while in OSPF, every packet needs verification. So overall, between routing protocols, if we go for authentication, here is done through HMAC for verification. So it's what it is, a hash with a pre-shared key. Because the original text, right, if you send it out and it's not encrypted, anyone can modify it. If you don't have the key, someone could alter it and then recalculate the hash. The recipient wouldn't know. So the sender includes a key to calculate the hash, and the recipient also uses a key for verification. This way, it's verified whether the data was tampered with. This is hashing, just hashing, right? These two things are not the same. One is a hash, the other is HMAC. Another one is called HMAC. They are not equivalent.